edition of the lesson on Williams Guide to Mathematics. We are taking a look at the topic probability in this lesson. However, it is a third lesson on the topic, meaning we've had two lessons before now, lesson 1 and lesson 2. In our lesson 1, we talked about facts about probability. We also talked about probability formula and we solved some problems. In lesson 2, we analyzed the concept of a coin, we analyzed the concept of a die, and we analyzed the concept of a playing card. We of course solved some problems involving all these three concepts. Now in this lesson, we are taking a look at combined probability. Under combined probability, we can have what is called mutually exclusive events, we can have independent events, we can also have dependent events. And we'll take a look at all problems on this, we solve problems on all of this. Let us start with mutually exclusive events. When do we say an event is mutually exclusive? Let me take the two keywords, mutually exclusive. I'll start with exclusive. When something is exclusive, it means not part of. Inclusive means part of. If I'm including something, that means that thing is part of it. If I'm saying exclusive or something is excluded, that means that thing is not part of. Now, mutual. When something is mutual, it means they have this benefit. They enjoy this benefit together. They go together. Now, look at the two words. It means they are contradicting each other. They go together, that means that's mutual. Then not part of, that is exclusive. But they are not contradicting each other. What we are saying here is that we can have the same source, which is explaining the word mutual. We can have the same source. We can draw out the same event from the same source, but one does not affect the other. We can draw out several events from the same source in such a way that one does not have an effect on the other. So I can say mutually exclusive events are those events that have the same possible outcome, but the required outcome cannot happen at the same time. Take for example, if I'm talking about vowels and consonants. Vowels and consonants are gotten from English alphabets, so meaning that they are mutual. But I cannot be talking about the vowels, the letters that are vowels, and be talking about the letters that are consonants, because they are not the same thing. Picking a vowel has nothing to do with the consonant. The same thing, picking the consonant has nothing to do with the vowel. So I can tell you that the vowels and the consonants are mutually exclusive events when talking about English alphabet. Also talking about numbers, I can take even numbers and odd numbers to be mutually exclusive events because they have nothing in common, but they are both numbers. They are both numbers, take them to be mutual. They have nothing in common, takes them to be what? Exclusive. Now, in set representation, we can have a universal set, we can have a subset A, as you can see, another subset B. The fact we said that they are mutually exclusive events means they have nothing in common, meaning these two sets will not join each other. The two subsets A and B will not be joined together. For that reason, we can take them to be a disjoint set. So set-wise, I can take the probability of A union B to be equal to probability of A plus probability of B, because they have nothing in common. Probability of A plus probability of B. Now, let me give you the formula for a case where we have not mutually exclusive. We can have a case of not mutually exclusive. That means they are mutual, but something is common to them. Take for example, if I'm talking about prime numbers and odd numbers. Of course, prime numbers and odd numbers. 3 is a prime number. 3 is also an odd number. So that is not exclusive. They are mutual but not exclusive. So if I have a case of a question that is not mutually exclusive, let me consider event A and B, like I said earlier, for exclusive, for the one that is exclusive, the set representation, the two sets will intersect, they will meet. I mean the two subsets A and B. And for our probability of A union B, it will be probability of A plus probability of B minus probability of A intersection B. That is, it is the probability of what we have for A, what we have for B, minus probability of what is common to A and B. Let us take a look at one example on probability involving mutually exclusive events. In this question, the first part is asking us for the probability of getting 3 or getting 6. They are mutually exclusive events because getting 3 or 6 mutual from a die. Now 3, 6, they are separate events. They cannot happen together. If I should toss a die now, I cannot be getting 3 and getting 6 at the same time. So they are mutually exclusive events. Now 3, probability of getting 3 or probability of getting 6, that can be expressed as probability of 3 plus probability of 6. By the way, anytime we have or in probability, we add. So probability of 3, from what we learned in our second lesson, we have just 1 3 in a die. That is 1 over 6. The same thing for probability of 6. We have also 1 6 in a die. So that is 1 over 6. So we have 1 over 6 plus 1 over 6, which is 2 over 6. And that can be reduced to 1 over 3. The second question there says probability of 4 or 5. Almost the same thing as the first. Probability of 4 or 5 will be probability of 4 plus 5. Remember I said for all we add. How many 4 do we have in the die? Just 1. That is 1 over 6. How many 5 do we have in the die? Also 1, which is 1 over 6. So we do 1 over 6 plus 1 over 6. That is 2 over 6, which also can be reduced as 1 over 3. In that question, the last part says neither 6 nor 1. Neither 6 nor 1. That means we are not dealing with 6 and we are not dealing with 1. Now, if I add my die 1, 2, 3, 4, 5, 6, the possible outcome. If I take off 6 and I take off 1, what is remaining? It's remaining 2, 3, 4, 5. That means the question is indirectly asking me the probability of getting a 2 or a 3 or a 4 or a 5. So I can express that as probability of 2 plus probability of 3 plus probability of 4 plus probability of 5. Remember I said or we had. So probability of 2, how many 2 do we have in a die? Just 1, that's 1 over 6. Probability of 3, also 1 over 6, we have just 1 3 in a die. Probability of 4, 1 over 6. Probability of getting 5 in a die, we have 1 over 6. Now I have 1 in 4 places, that is 1 plus 1 plus 1 plus 1. That is 4 over 6. If I reduce that, I will have 2 over 3. Taking a look at independent events. Independent events can occur separately. So if I have two independent events, X and Y, I can say that they can occur without affecting each other. Again, independent events can occur without affecting each other. Take a look at these two events. A coin and another coin, meaning we have two coins. So the first coin will give me its own results. The same thing applies to the second coin. So in that case, I'll be having something like what you can see on the screen, the table you can see on the screen. We can have head, we can have head, tail, we can have tail, head, and we can have tail, tail. So in that case, we have 4 possible outcomes. But if the question, if I don't want to draw the table, if the question is asking me to get the probability of head, head, all I need to do is probability of head, head. Now, what's the probability of getting head the first time? It is 1 over 2. What is the probability of getting another head? It is also 1 over 2 from the second coin. So what I need to do here when it comes to independent events is we multiply. So anytime you have independent event, is also called the multiplication probability. So I'll just do 1 over 2 times 1 over 2, which is 1 over 4. From the table we have on the screen, you will see that the only time we have head is just 1. How many outcomes do we have? We have head, we have head tail, we have tail head, and we have tail tail. That means we have 4 outcomes, meaning the getting head is just 1 out of the total 4 outcomes. We can also have the case of 2 dice. The case of 2 dice. See the outcome on the screen. We have 1 1, 1 2, 1 3, 1 4, and so on like that, up to the last one, which is 6 6. So what is the total outcome we have? If you count all that we have on the screen, we have 36 outcomes. So the sample space for 2 dice is 36. Now, the question can come in any form. I can ask you, what is the probability of getting a sum of 7? Probability of getting a sum of 7. Now, what are the values that can give me sum of 7? If you check from the top, from the first row at the extreme end, you see 1 6. If you check diagonally below it, you see 2 5. You will also see 3 4. You see 4 3. You see 5 2, and you see 6 1. If you count all that, that is 6 of them. So the probability of getting a sum of 7 is 6 over 36. So also, I can be asked to get the probability of getting a sum of 10. What are the sum that will give me 10? I can have 4 6, I can have 5 5, and I can have 6 4. 4 6, 5 5, 6 4. They will give me 10. That is 3 over 36, which is 1 over 12. The question can also ask me to get the probability of getting the same digits. The same digits. That one is straightforward. That one is just 1 1, 2 2, 3 3, 4 4, 5 5, 6 6, as you can see in the table. So in that case, we have 6 required outcome out of the 36. That is 6 over 36, making it 1 over 6. You can also have the probability of getting 2 prime numbers. You can see the prime numbers as indicated on the screen. 2 prime numbers. We can have 2 2, we can have 2 3, we can have 2 5. We can also have 3 2, 3 3, 3 5. And we can have 5 2, 5 3, 5 5. Meaning we have 9 required outcome based on our question of 2 prime numbers. The prime numbers between 1 and 6, they are 2, 3, 5. So we can have 9 possible outcomes, and that is 9 over 36, which is equal to 1 over 4. Now I have talked about 2 coins. I've talked about 2 dice. I can also have a coin and a die. Now, if it is a coin and a die, let's say the question is probability of getting a head and a 3. Probability of getting a head and a 3. The probability of getting a head is 1 over 2 because the coin is having 2 sample space. The sample space for the coin is 2. So, and the probability of getting head, we have just 1 head, that is 1 over 2. Then the probability of getting a 3, we also have 1 3 in a die, that is 1 over 6. And remember, I told you, when you talk about and in probability, we multiply. So 1 over 2 times 1 over 6 will give us 1 over 12. Again, 1 over 2 times 1 over 6 will give us 1 over 12. I can also have another question like probability of getting a tail and an even number. Probability of getting a tail and an even number. The question is, how many tails do we have in a coin? It is 1 out of 2. How many even numbers do we have in a die? We have 2, 4, 6. That is 3 numbers. That is 3 over 6. So if I multiply that, 1 over 2 times 3 over 6, that is 3 over 12, which is equal to 1 over 4. Let's take a look at this example. The first thing we need to do is to take the sample space. 3 plus 5 plus 7, that is 15. Now the question is asking for the probability that the first is blue and the other is green. The question is, how many blue do we have? We have 3 over 15. Multiplied by how many green do we have? We have 7 also over 15. Now if I reduce 3 over 15, I have 1 over 5. So if I multiply my result, I will get 7 over 75. 7 over 75. In this second question, we are asked to get probability that one is blue and the other is green. It is a bit different from the first. Why? Because in the first case, the question specified that the first one must be blue. Now in this case, there's no such specification. So we can think of it that we can actually have a blue first and a green second, or a green first and a blue second. So you can see it is quite different from the first one. The first one, the question specified that the blue comes first, then the green will be second. But now there is no specification of such. So we need to assume that we can have blue first, green second. We can also have green first, blue second. Now for blue-green, that is blue first, green second, we have 3 over 15 multiplied by 7 over 15. While for the other one, green first, blue second, we have 7 over 15 multiplied by 3 over 15. Mind you, because we have all between them, it will be a plus. So I can take that to be 3 over 15 times 7 over 15 plus 7 over 15 times 3 over 15. That will be, for the first part, 21 over 225. And for the other part, 21 also over 225. That will give me 42 over 225. 3 in 42 is 14, and 3 in 225 is 45. The third question there says they are of the same color. They are of the same color. That means we can have blue and blue because we are picking two balls. We can have red and red. We can also have green and green. So blue, blue, or red, red, or green, green. Now blue, we have 3 over 15 because we have 3 blue balls. We repeat that times 3 over 15. Plus, from the or, that of red is 5. So we have 5 over 15 times 5 over 15. Plus, that of the green, 7 over 15 times 7 over 15. So if I multiply 3 and 3, I have 9 over 225. If I multiply 5 and 5, I have 25 over 225. If I multiply 7 and 7, I have 49 over 225. Now, 9 plus 25 is 34. 34 plus 49 is 83. So I have 83 over 225 as my probability of picking the same color. For dependent events, there are events that affect one another. Unlike independent events I told you earlier, that they do not affect one another. Now, another good example, another good way of getting independent and dependent events is that independent event comes in the form of with replacement. With replacements. Take for example, in a basket, I have 3 blue and 4 red. With replacement, if I pick my first blue ball out, if I'm to pick the second one, I'm going to replace the ball. So I'm having 3 and 4 before. So I'm replacing it back. It's as if nothing has happened. So if my first probability of picking a blue ball is 3 over 7, the second one will also be 3 over 7 because it does not affect anything. You know, I said independent events, they do not affect one another. But the same thing is not for dependent events. For dependent events, they affect one another. If I'm picking the first blue ball out of the 3 blue and 4 red, which is 7 in total, if I'm to pick the second ball, my second ball, I will be considering 2 blue now, because the blue balls have been reduced by 1 based on my first pick. So I'll be having 2 blue and 4 reds, meaning the probability of picking the second blue will be 2 over 6, because the total ball has been reduced by 1. So for dependent event, we consider the fact that such an event will be without replacement. I'll repeat the same example I did for independent events earlier. Let us look at that same example. We have 3 questions under the example. Remember, in the example, we have 3 blue, 5 red, and 7 green. But the major difference between this example and that is that in this example, I'll be considering without replacement, which explains dependent event. Now, like we did for the first one, we add all the given number of balls, which is 3, 5, and 7, and that will give us what? 15. Having done that, let's start. The first question says probability of getting the first as blue and the second as green. Now, my blue, how many blue do I have? I have 3 out of how many? 15. Multiplied by, now how many green balls do I have? I've not tampered with my green. All I picked at first was blue. So the number of green I have is still intact, meaning I have 7 green over. Now, what is the total ball? Remember, I have picked a ball earlier, which is a blue ball. So I'm not having 15 ball any longer. I'm having 14 now, because the number of blue that is left is 2. The number of red is still intact because I didn't touch red, is 5, and the number of green before picking this one is 7. That makes 14. So that is 7 over 14, meaning the probability of picking a blue and a green based on the without replacement concept, it will be 3 over 15 multiplied by 7 over 14. Of course, 7 can cancel 14. 7 was 1 over 2. The same thing for 3 over 15. That is 1 over 5. That will give 1 over 10. The second example there says the probability of picking 1 blue and 1 green. Like we did for the previous example, we said they are not exactly the same question, because this second question is not specifying which of the 2 balls will come first. So I need to do a permutation on that. That means I can do blue green or green blue. So let's take it. For blue, we have 3 over 15. For green, we have 7. Remember, we picked the ball for blue, so the total is now 14. No more 15. So we have 3 over 15 times 7 over 14, or which is plus. Let's go to the other one. For green, which we are starting with this time, it is 7 over, I've not picked any ball, so that is over 15, multiplied by, now for blue, I've not picked any blue, so my blue still remains 3 as given in the question, divided by, I've assumed that I've picked a green ball, so the total number of balls will reduce by 1. Initially it is 15, but now it is 14. So I have 7 over 14. So from what I have 3 over 15 times 7 over 14 plus 7 over 14 times 3 over 15. What will that give me? 3 times 7 is 21. Now 15 times 14 is 210. So I have 21 over 210 plus 21 over 210. That is 42 over 210, which is 1 over 5. Finally, let's take a look at the last question, which is probability for the same color. I can have probability blue blue, or probability red red, or probability green green. Now, for probability blue blue, I have, for the first blue, I have 3 over 15 because we have 3 balls that are blue. Now, picking my second blue, I will assume that 1 blue is gone, so remaining 2 blue. That makes it 2 over 14. Now let me go to the next one, which is probability of picking the red. We have 5 red at first, So we still maintain our 5 for the first peak over 15. Multiply by now. One red is gone, meaning we have 4 more left. So 4 over what? 14, because the total will also be reduced by 1. And the last color, which is green, we have 7 green balls over 15, the total, times 1 green ball is also gone, meaning we have 6 over 14. So if you multiply all that, 3 times 2 is 6 over 210, plus 5 times 4 is 20 over 210, and then 7 times 6 is 42 over 210. So if I should add 6 plus 20, that is 26. 26 plus 42, that is what? 68 over 210. If I should divide that, I will have 2 in 68 is 34, and 2 in 210 is 1 over 5. So I will have 34 divided by 105. Finally, we've come to the end of the lesson 3 of probability, which happened to talk about combined probability. Under combined probability, we focused on mutually exclusive events. We also talked about independent events, and we talked about dependent events. We still have a lesson after lesson 3, which is lesson 4. Not to miss out on the lesson, subscribe to the channel, Williams Guide to Mathematics. Get all the videos on probability, not just all the videos on probability, all mathematics topics videos from this channel, so that you make your understanding of mathematics very good. I'll see you very soon.